Hello everyone, good morning and welcome back to this training on machine learning with Python. We've covered interesting topics so far and we'll be doing a lot more this week. This is Sanket Sarang again. I'm one of the founders of Blobcity and I have Suveer Bhatia with me also, who's founder of What If Realtix and our trainer for today. Suveer is a prolific trainer. He's trained for several large companies and an expert in data science and worked on several data science projects. We started off last week with the first batch, and this week, Saturday is the second batch. So this is same format as last time, wherein we will cover 4 sessions over the weekend, 2 hours each. So in Indian time zone, it'll be 11 a.m. to 1 p.m. today, India time, and after that we take a break from 1 p.m. to 2:30 p.m. and then we resume again at 2:30 p.m. And end at 4:30 p.m. So 2 hours, 2 hours in the morning, 2 hours in the afternoon, total 4 hours on Saturday, 4 hours on Sunday. Some of you have joined in new, so a lot of you might have come in since last week. Some of you might have joined in only this week. You were not able to attend the training last week. So for all those, if you have missed anything, you can register onto the Blobcity Cloud. There's a handout section which has setup instructions. Simply download the PDF. You would have also received the setup instructions over email. So I recommend downloading the PDF, following the PDF. It has everything necessary to get you set up onto the platform, and create your cloud book and keep your code ready so that you can start coding along with Suveer during the training. If you must go back and watch a recap, you can go into the Learn section. You must be on a paid plan to do so. You can activate it and you can watch a recap of the training for all those who missed it last time. For all of you who have been joining since the beginning, you will find it extremely easy to kind of continue on and follow the training. So without further ado, let's get started. I have Suveer. Suveer, over to you. You can take the session. Suveer, you're on mute. If you're talking, we can't hear you.
No, I'm on. Thank you, Sandeep. Thank you for the introduction. Welcome, guys. For a rollover session from the last weekend, so a lot of people must have been there from the same batch in today's session. I hope some people are also new, so I would still encourage them to continue with the session because today we're going to learn some fundamental parts of machine learning using simple examples. We'll not try to complicate it too much. We'll try to understand some of the algorithms and the science behind those algorithms. So just a quick recap and just a quick thing about what we did last time and what are we going to do today. So that is basically going to look at in today's session. But I had also sent a quiz on the last time session, and also there was a small assignment. So in case for people, those who did not receive the quiz, I have it in front of me right now. But before we attempt the quiz, just a quick recap on what kind of algorithms basically we covered. So I'm going to quickly go on to our next slide, which is basically going to talk about something. So this is an introduction slide. So yes, hope you're doing good and you're back in the session for the spirit of data science. We will see some examples, some classification using naive Bayes, logistic regression, etc. Jumping to the day, actually this is day 2 slide. So what we did, it was a recap of simple linear regression, naive Bayes, Gaussian naive Bayes we had studied. Then we also looked at classifying handwritten digits. So far, we have seen algorithms on classification and a small example on clustering, which is actually supervised machine learning. So what I understand from this class so far that we now know what is the difference between a supervised machine learning and an unsupervised machine learning. Okay, and we have been focusing so far on classification techniques, and today also we're going to focus a bit on classification techniques. And this time the training is going to be a bit different. I'm going to basically create a new notebook rather than pre-writing the codes in that. I will write the code right in front of you so that you can practice it parallelly along with me. Okay, so I will toggle between the questions, and periodically I will come back so that I'm able to address you all. So I can see a couple of names. I have Vinayak Shukla, we have Venkata Reddy, Naveen, Shivantanan, welcome Naveen, Arun, welcome Arun, Amit Chokshi, welcome back Amit Chokshi, Saptashri, welcome back Saptashri. So Siska, quite a good people we have following up from our last batch. Nagesh is there, so thank you all for joining back this session. All right, so Malam Ikban Reddy says, I'm a fresher. Can I get before week recorded videos? Yes, sure. So you have to register with the Blob City, cloud.blob city, and you can access the pre-recorded sessions. Yeah, so you will get the notebook after the class, Shreyansh. Okay, so let's quickly go and look at the Nulu Rangamandu says, today is my first class, and Guru Raj says, hello. So hello, Guru Raj. Okay, so let's quickly go and look at the the quiz and the assignment which we did basically on classification and clustering, etc. Okay, so I'm going to just go back into my slides. So quickly we will solve this quiz and then we'll go on to our new topics for today, which I'm going to show you that in a moment. So Bhagwan saying, good morning. This is my first session. Hope that will be helpful for me. Yes, Bhagwan, our mission is to basically make data science simple for people. All right, so yeah, okay. So let's begin with this quiz. So in simple linear regression, we generally have more than 2 independent variables. So the first answer is actually false. Rupesh has said true. Siska and Kunal is saying false. So Arun saying only one, Sandeep saying false. So very good. So we have majority of the answers coming as false, and the actual answer is false. So in simple linear regression, we generally have 1 independent and 1 dependent variable. Okay. So the answer to the first one is false. So, second one is spam detection or image recognition fall under machine learning using clustering. So is that answer spam detection or image recognition is actually not clustering? It is false. So most of the people have said false. Ronald Raj says true. No, it's actually false. Shubham Kumar says false. Lalit says false. Absolutely, very good. So moving on to the next one. Let's go with the support vector machines. So SVM, nearest neighbors, random forest are all learning methods for classification. Is that true? Okay, great. So fourth one, naive-based methods are a set of supervised learning algorithms with a naive assumption of conditional independence between features. True. Okay, great. True, very good. So one of the major disadvantage of using the holdout set for model validation is that we lose a portion of our data. Is that true or false? So is that true? So even fifth one is true. Very good. So sixth one is, that's very nice, Arun. Sixth one is a stockbroker wants to create 3 major clusters of company stocks and label them as given. So which learning method he should use? Naveen says classification. Any specific reason for classification? Arun says clustering. Nisha says classification. Any specific reason for classification? Why are we going to classify the stocks? We are going to classify the stocks based on average returns, low returns. We'll see basically this is quantitative. So we like to cluster these stocks first and create a group of clusters. And later on, after creating a group of clusters, we can decide if you want to further classify it or not. So yes, Komal Parab, Guru Raj, Sujit, Priyanka, Nivitha, Sushil, yes, you all have given the right answer, and it is clustering. So in statistics, p-test, z-test, t-test, and all categories are all categories of inferential statistics. Question number 7. So true, don't know. Sunkara, don't know. Okay, true. So basically, these are the tests for validations in statistics. So if you want to compare the differences of one group with the other, then we are going to use these statistical tests. Okay, so the answer is going to be true. So in machine learning, predictor variables are often known as independent variables. Is that true? Nagesh says, Mahesh says false. Any specific reason? It's true. So the actual answer is true. Okay, so question number 9. In linear regression, when we say fit the model to the data, this is where the machine actually starts to learn. Is that true? Question number 9. Very good. All right. So false is being said by Ronak. No, not Ronak. Mahesh. Any specific reason? Prince Kumar says false. Now, this is where we fit the model. So that's where exactly the OLS regression or the regression starts to take place. And the actual answer is true. 10th one, clustering is a technique in which data is automatically assigned to some number of discrete group of clusters. Is this true? So most of the answers in this question set is actually true. So Nagesh, yes. Amit Chopsi, Vikas, Pratibha, Priyanka, Arun, yes. Porsha, Nevita, yes, that's right. So answer is absolutely true. So now based on this technique, we're going to move forward and going to solve some simple examples on machine learning. We might take up our basic data sets of maybe a 1 variable or maybe a 2 variable, and we'll try to see how we are actually going to predict and what is the science behind predicting. So the answer for the 9th one, Shweta, is true. Yes, Siska, definitely. I will share the materials with you. Let's go and look at the assignment. I'm not sure how many people have finished the assignment. Any updates? Any hands up for people, those who have submitted the assignment? Anybody? Didn't get, okay. First day, okay. Only quiz, okay, no problem. Announced received, okay, no problem. Sure, okay, fine, guys, no worries. So earlier, so we have solved using iris data classification using Gaussian namebase. Okay, so for the people, those who are into this session for the second time, no problem, Kriti. You will soon receive these assignments. So we have solved iris data classification using Gaussian namebase. Okay, and in the last session, we just wrote a simple code for Gaussian namebase. In the last sessions, in fact, I wanted to just show you, the basic parts of machine learning like Gaussian namebase or maybe, SVM or any other kind of part which we have seen, just for kind of getting familiar with the starting of machine learning. But today we're going to look at it really from the engineer's point of view. So anybody can tell me what is Gaussian namebase? So the assignment here is that initially we have solved questions using, of course, iris dataset, but we have solved using Gaussian namebase. Okay. So what if instead of Gaussian namebase we are trying to use logistic regression? So let's go and we can do this part, and we can also check the accuracy over there. So we won't spend much time on this slide. So let's say what we have for today. So we're definitely going to look at some of the algorithms. So types of classification, as I said, guys, I'm focusing on supervised machine learning today, and even tomorrow's half session is going to be supervised machine learning, and after the second half is going to be unsupervised about k-means, clustering, etc. So simple linear regression, naive-Bayes, multinomial naive-Bayes, logistic regression, multinomial logistic regression. And today we have also an activity on support vector machines, if time permits, to basically classify the faces, the database of faces which we have with us. Most of the data sets which we're using will be from sklearn. So as you know that we are using sklearn library API from Python to do the machine learning. There are many aspects of this, like creating pipelines, regularizations, tuning hyperparameters, some of the things which we have not seen in these classes, but moving forward, definitely we are going to do a lot of sessions on these things, like how to create a machine learning pipeline, etc. So let's go ahead and start writing this code. So I'm not going to write code right now for linear regression. I'm going to start with what we did exactly in day one, and then I'm going to come back. I've already written the codes on my notebook, but I'm going to open a new notebook right now. And you would see that I have also opened, if you can see that I opened some of the Wikipedia links over here, because I would want to show you some of the references in the Wikipedia link. I will keep toggling between what is given in Wikipedia and how are we going to relate over to us. Okay, so let's get started. So this is basically our day number 3, and we're going to study about naive. Okay, naive is a probabilistic model, and we're going to study about logistic regression. Guys, I would encourage you to code along with me so that you're also able to get hands-on to these sessions. I'm going to just go to Untitled 1, and I'm going to say day 3 I already have, so I'm just going to write day 3 underscore revise for now. Okay, so let's first understand that what data set we had dealt before. For people, those who are thinking that we are going to still work on basic data sets, actually we are working on basic data set because that's going to clear the fundamentals. Okay. Arvind's question is, what is the difference between naive-Bayes and multinomial naive-Bayes? Today's first half, before the lunch, I'm going to cover up that part, Arvind. So please, you can listen to this session intently, and you can start practicing along with this. So what did we do? So first, we wanted to import some data set. Okay, so I'm going to say that I want to import some data set. I'm going to use it from my SNS. Now SNS is nothing but, so I'm going to say SNS dot load data sets. Okay, so this is not going to populate because I've not loaded the SNS. So what I can do is, so import Seaborn as SNS. So this is the library of Seaborn. And then I'm going to say, I want to load the data set. By the way, I'm using this Jupyter notebook, so you can use the same thing. And I would encourage you to use the same link, that is cloud.blockcity.com, just to be on the same page, because we have updates of libraries and frameworks, which is already happening on this platform. So in case if you're using your own local version, that may differ in terms of library version, etc. So I'm going to say I want to load some data set, and the name of the data set is going to be, there are many data sets, so I can just type in what kind of data set I want. So I'm going to say I want basically an iris data set. Okay, and after this iris data set, I would like to explore some of the things. So this is like a pandas data frame. I'm sure people know what pandas data frame is. Now, if you look at this data set, there are 5 odd variables out here, right? So what is the function if I want to see all the column attributes, or basically the data type? So I'm going to say that you give me the info, and in this data set or this data frame info, I want to see that what are the column types, what are the data types of these columns basically. So I have got float around, float 64 for 4 features, and one of the dependent variable is actually species, which is an object, which is actually a categorical. Now, when we look at this data set, okay, so when we look at this data set, our assumption is that we have this data set available with us for training, and we would like to predict these species over there. Now, in past session, we had used Gaussian naive-Bayes, so I'm just going to work on that Gaussian naive-Bayes. But if you remember our machine learning steps, could anyone tell me the machine learning steps which we had used earlier? So the first step which we are going to do in machine learning is load the data. Is that correct? Load the data. What is the second step? What we're going to do? Load the class. Okay. And what is the third step? Instantiate the class. So instantiate the class maybe in terms of tuning hyperparameters. Correct. And the last but not the least, we have the predict class. So basically, we predict using the test data set. All right, so these are the steps which you have studied that instantiate the class. You basically tune the parameters if there are any for your logic, and then you basically fit the model. Okay, this is actually where the regression takes place. Fit the model, and then you predict from the model. Okay, so this is what we had studied in the previous session. So let's go and try to implement this inside our Jupyter. But when we reach to this stage, that is after loading the class, when we are actually instantiating the class, or when we are fitting the model, there is one more requirement that our x value has to be two-dimensional and our y value has to be one-dimensional. So do you guys agree with this particular statement, what I have written here? Okay, Vikas Kumar says yes. Amir says yes. Welcome back, Amir. Kunal says yes. Sandeep says yes. Okay, that's great. So we know that our x has to be two-dimensional and y needs to be single-dimensional. So how do I transform that data? Okay, so I'm going to say x underscore iris, and that's okay. Iris I already have as my data set, so I'm going to say iris dot drop. Drop what? Of course, I want to drop species. So I hope I'm going to get the column for iris dot drop. Okay, not able to get that. So CIES, and then I want to say since now drop is a pandas data frame functionality, I want to say that you drop the column species or you drop the feature species, and the access for it to drop is going to be 1 because we have to specify the access for this kind of things. And let's see what we have in x underscore iris. Definitely now, compared to the previous data set, we just got only quantitative information in this and nothing else. Okay, so I'm going to go to cell, current output, I'm going to say clear. So x underscore iris, actually this is the independent variable. Okay, quickly I'm going to finish this so that we understand other topics. And then we need to create a y. So how do we create a y? So we're going to say y underscore iris. So that means in y, we should have nothing else. We should have nothing else other than iris species. Okay. So y underscore iris is ready, but we still need to check the shape. So x underscore iris dot shape. We're going to do y underscore iris dot shape. Let's see what kind of shapes we have. So y is a single dimension. Can you see? There's a single dimensional data which is suiting our requirement. X, if you see, it's a two-dimensional. So x is also suiting our requirement. So our data set is ready when we have x as in a feature variables. So this is going to be feature variables, and this is going to be our dependent variable. Okay. So how do we fit this data? We can definitely go and preview this, but how do we fit this data? We're going to fit this data using either Gaussian naive Bayes or logistic regression. I'm going to explain you why we're going to use Gaussian naive Bayes or logistic regression for that matter. But before we fit this, so what are the second steps? So we have loaded the data. We have loaded the classes. We have loaded the data. We just loaded X and Y. We have not loaded the class, nor we have fit the model. But in order to basically fit the model, we're going to create some kind of availability of the data. Okay, so I'm going to say, since we're using sklearn, I'm going to say from sklearn model selection. Now, this is a method in sklearn model selection. We're going to import some part of that. What do you want to import? We want to import train test split. Now, what is a train test split? We have seen that it's going to create basically 4 different variables for us, which is x train, x test, y train. For people, those who are unable to follow this can ask me questions and I'll be happy to answer this. So train test split. Now what this train test split function is going to do is going to create 4 different variables for us, or with with some partition size over there. Okay, so what is my real data? My real data is x_iris, and what is my test data, which is y_iris. If you could see, we have created this here. Okay, and what are the other parameters? I'm going to say random state. Random state is equal to 1. So random state basically is going to take the data randomly, and it's going to give us, so random_state. So if you look at xtrain or xtest, this might have around 80% of the data which we have over there. Okay, so our data is ready for xtrain, xtest, ytrain, and ytest. Now, what is the second step? When we have loaded the data, we have to load the class. Okay, so what is the class? So let's say we want to solve this example using two methods, and I want to highlight something about this part. Let's say when we go to this slide, okay, I'm actually writing this slide and nothing else. So let's look at this slide. So earlier problems we have solved using naive Bayes. Precisely, we're using Gaussian naive Bayes, where we had 4 features and 1 output. And we did this using our iris data set. So on the right hand side, if you see, we have already done this in our previous session. And on the left hand side, if you see, this is something which we can look into today. But if you look at the accuracy of these two models, there is not even a slightest change in the accuracy. So if I basically classify species using Gaussian naive Bayes, I'm going to get an accuracy of around 97.36%. And if I'm going to use the same data set on using a logistic regression, then I'm going to get almost the same accuracy of 97.36. Now, why this is different over here? That is something which I will explain you. Okay. So let's go back to our coding area. Now we have collected the data. Now we want our class to be initiated, right? So what kind of class we want? Either we can go for a Gaussian naive Bayes or logistic regression. I'll first go with Gaussian naive Bayes, and then we will go with logistic regression. Okay. So, and if you can recall, both Gaussian naive Bayes and logistic regression fall under linear models of sklearn. So I'm going to say from sklearn.linear model. Can you see over there? The method is linear model. I'm going to say you import Gaussian naive Bayes. Gaussian naive Bayes. Okay, let's see. Import sklearn linear model, GAUSSIAN. Sorry about that. Extremely sorry. We have a method as naive Bayes and not linear model. So we have naive Bayes. I'm using sklearn naive Bayes. Yes. Okay. I won't say import Gaussian naive Bayes. When I'm writing a loss regression, I'm going to use a linear model. When I'm going to use a Gaussian, I'm going to use a naive Bayes, because Gaussian naive Bayes is actually based on Bayes theorem. So when I'm going to run this, I'm going to import the Gaussian naive Bayes method in this class. Okay, so what is the next step? So when we have initiated this naive Bayes, I've imported this Gaussian naive Bayes. The next part is basically to tune or bring the hyperparameters. So model is equal to Gaussian naive Bayes, and I'm just going to load this as it is. So the model has got the parameters for the Gaussian naive Bayes, and I'm going to say model.fit. So model.fit is basically where we actually train the model. So model.fit, the first argument is going to be our 2D training features, and this is going to be our 1D. So xtrain, and then so we have got here xtrain and then ytrain. Okay, so I'm going to use Y train out here. So I'm fitting the model. So actually this is doing a quick machine learning. Here actually the model starts to learn. So the model will analyze all the RHS, that is all the 2D features, and it'll just analyze it against the dependent variable over there. Okay. And I'm going to say, so model is going to be fit, and what is going to be the next part? I'm going to predict using the model. And if you see the arguments to predict function is basically model or predict and the X, so perform classification on an array of text vectors. Now, if you want to see the help, you can simply go inside this box and say shift and tab. So when you use the shift and the tab key, there is a help which gets pulled up. You can quickly check for the argument. So, here it is saying that what is your argument? And this time my argument is going to be X test, because that is where my test data actually resides. Okay, so if you see the output now, it is giving us all the labeled data out here. So basically, I'm assuming that some input was given to the model, and the output is actually categorized labels. If you see, but it's very difficult for me to manually look and check for this part. So what I'm going to do is I'm going to import some form of accuracy which we had seen last time. So again, from sklearn, now accuracy comes under a class of metrics. So I'm going to say import accuracy score, and then I'm going to say accuracy score of what I want. Accuracy score of test. I want accuracy score of Y test. So Y test is basically going to be here, because accuracy score, I want to compare what is the test data, which is Y test, and what is the predicted model. My predicted model is model.predict. X test is actually basically my model of predict. So I'm going to say, I'm going to put this into Y underscore model, which is actually my predictions. And this is going to be, I want to say, compare my test data set with the model which I've created. And if you see, my accuracy score is coming to 97.36%. Now, this is the accuracy score when we have used iris data classification using the Gaussian name base. And I'm going to talk about what is a Gaussian name base and what is a name base. But let's see if we are able to do this using our logistic regression. Okay, so same things. So we're going to say from sklearn. I wanted to demonstrate this quickly, and because we have a lot to cover, and we're going to say logistic regression. Okay, now instead of we importing a Gaussian-based methods or a distribution over there, I'm going to use a logistic regression, which is going to be just same as what we did earlier. And model is equal to, I'm going to say logistic regression as a function over there, because I'm actually importing that into the model. And same, no, nothing different, model dot fit X train, comma Y train. Okay, and then I'm going to say Y underscore model is equal to model dot predict, and predict what? X test. So it looks good. Let me run this. Okay, so when I run this, it is basically training our data set, which we have given in X train and Y train, into the logistic regression. But it seems to be there is some kind of warning messages, increase the number of iterations. Okay, so no problem. What happens is sometimes based on, let's say I want to just put up an argument, max iterations, let's say I want 200. Okay, now since this is a regression, definitely we need higher number of iterations. So depending on the size of the data, we have to set this parameter. So this is one of the, what I'm tuning. So same things, there's no difference. So again, I'm going to say accuracy score, and this time, let's say I want accuracy score of Y test again. Accuracy score of Y test again with Y underscore model. Now this time Y underscore model is actually the logistic model and not the naive-based one. So if you see now, both the accuracies, 97.36, 97.36, they're exactly same as what we have done before. Okay, so whether we use a Gaussian naive Bayes or basically logistic regression, we are getting the same output. But how? How is this happening that we're going to get? And in what cases we should use logistic regression, and in what case we should use linear models? In which case we should use naive Bayes, and in which case we should use logistic regression? This is what we're going to do just moving forward. I'm going on to the question side, and just to see if any questions are coming. Please explain what is sklearn naive Bayes. Jeevan and Rajiv, how to install uh, Neha Ranjan, you can ask the questions with the trainer on this chat box. Sandeep says, why test, why model? Where do we get these PPTs? PPTs have been shared with you, so you can have it in your portal. Suyash says, fixed. Okay, so I didn't get through all the questions. So can we get today's? Okay, so not much of the questions. It seems like a lot of questions are from the environment perspective, not getting the notebook. Okay, so guys, whatever we have covered so far, any questions on that? So I have a question. So when to use Gaussian naive Bayes and when to use logistic regression? Can you answer this question? Oh, another question is, can Gaussian naive Bayes have more than two dependent classes? Can logistic regression have more than two classes? So can you answer this question? Simple questions. When to use Gaussian naive Bayes and when to use logistic regression? Gaussian naive Bayes, okay, I've not seen the answers. Anything is not free. Should we have to? Where I get PPT max iterations for better accuracy. So logistic regression is binary in nature. Pramod says logistic regression has two classes. Yes, Pramod, you're right. Logistic regression has two classes, but it can have more than two classes also, and that basically falls in multinomial logistic regression. Karan says logistic is binary in nature. Okay, fine. So couple of inputs, but let me tell you, whenever we are using a Gaussian naive Bayes, whenever we have the independent variables, okay, as continuous, okay, or have a Gaussian distribution. Guys, anyone understands what is Gaussian distributions? So we're going to use Gaussian naive Bayes. I'm going to remove this logistic regression. So we are going to use Gaussian naive Bayes when we have independent variables as continuous, or they have a Gaussian distribution among themselves. Okay, so or have a Gaussian distribution. I'm going to elaborate on this point. Can Gaussian naive Bayes have more than two dependent classes? The answer is yes. So in our iris dataset, we actually created species of three class. There's species attribute of three classes, so we use Gaussian naive Bayes to do that. Can logistic regression have more than two classes? Yes, in a multinomial logistic regression. Okay, so yeah, so this is basically the thing over here. But if you look at the Gaussian naive Bayes, Gaussian is same as a normal distribution. Yes, that is correct, Arvind. But what is a normal distribution? Normal distribution is a Gaussian distribution. Yes, that is correct. And Gaussian distribution is a normal distribution. But what exactly is a normal distribution? Ayush Saxena says mean of 0 and so Ayush says and a standard variance of 1. So that is correct. So whenever we have a mean of 0 and a standard deviation of 1, we are saying that we have a normally distributed data. Now, whenever we have independent variables as quantitative, that is continuous, it is an assumption. In fact, I would say it is a naive assumption that the distribution is normal in nature. That's the reason the algorithm is called as naive Bayes or Gaussian naive Bayes. Gaussian naive Bayes because naively assuming we are naively assuming that the distribution of the independent features are normally distributed. Okay. Now, it is always a good practice to basically do the EDA part, that is exploratory data analysis, before we consider the features for our training data set. But this, yes, that is one of the, we can also do principal component analysis basically to get that kind of outputs. Which model to use when independent variables are a mix of continuous and discrete? So Ritu has a question. So when we have, she's asking whether to use a Gaussian naive Bayes or log. See, whenever we have independent variables as a mix of continuous and discrete, but what is your output variable, Ritu? So what is output variable? Is a binary or output variable is a continuous? Okay, that depends on, yeah. So Kritika says bell curve. Exactly. So Kritika says bell curve. So whenever our distribution is actually forming a structure like a bell curve, that's where we have a normal distribution. So let's have a look at how does a normal distribution look like. So this is what we have done. So we have used both logistic regression and Gaussian naive Bayes to get the accuracies. And moving forward, we're going to see this in detail. Okay. This we have already seen. Now, let's understand Gaussian naive Bayes. So it's important. So we have understood so far why it is called as Gaussian naive Bayes. It is called as Gaussian naive Bayes because it is normally distributed. The assumption, the naive assumption is that it is normally distributed. We have other forms of naive Bayes algorithms like multinomial naive Bayes, which we're going to see right after this example. So this example is on Gaussian naive Bayes, wherein we are trying to predict using continuous independent variables. The other one is going to be multinomial naive Bayes, wherein we are going to consider the frequency of occurrences of each event into a class. So that's what I'm going to talk about. So, but first understand what is a naive Bayes. So naive Bayes classifiers. Now, after this activity, and I want you guys to be very attentive and listen to this intently, because if you understand this part, after today's lecture, I'm sure that given any data set to you, you'll be able to create your own classifiers in supervised machine learning. So naive Bayes classifiers are a family of simple probabilistic classifiers based on Bayes' theorem, with a strong assumption that the features are independent of each other. In case if you have a problem understanding these statements, you can put that into the question box and I'll try to elaborate for you. Second, it is a set of supervised machine learning algorithms based on Bayes' theorem with the naive assumption of independence between pair of features given the value of that class. Third definition of naive Bayes is naive Bayes classifiers are scalable and they require very few parameters basically to basically create the class and then create a model out of that learning problem. So naive Bayes is simple, but now naive Bayes, at a very hypothetically, we've understood what is a naive Bayes, but let's understand what is a Gaussian naive Bayes. So when dealing with continuous data, our assumption is that the continuous values associated with each class are distributed according to a normal distribution. So can you see these images in the bottom? So if you look at these images in the bottom, we will see that the structure of these images are looking very much same. They are more or less looks like normally distributed. So if you look at sepal width, the data looks like it's kind of forming a bell curve. If you look at the sepal length, more or less like a bell curve. Petal length, yes, both the distributions if you see are like normally distributed. And even in petal width, we have normal distributed data sets over there. So how do we create this? So how do we create this in Python? So let's go ahead and start our coding. And this is going to be insert cell below. I'm going to say checking the distribution of a continuous independent variable. Okay. And what is our data we have? Iris.head is our data set. So if you see, we've got, so we want to check what is the distribution of each of these variables, so that, once we are able to get the distribution, we can check whether it is normally distributed or not. And once it is normally distributed, we can use a Gaussian name base to do that. Okay. So I would like to basically use bar charts, which we have seen in these slides. So I will import what? Matplotlib.pyplot as ELT. So this is going to give us flexibility of, creating some charts. Let's work on single charts. I'm not going to create a subplot over here. So using a matplotlib, so I'm just going to create a single plot. So first I need to get the value, single value. So these are like the statements which I'm writing right now, guys, is from the pandas library or pandas API. So if you are familiar with pandas, this will be quite known to you. Otherwise, you will also have to come for the Python, pandas and NumPy classes. So x is equal to iris. I want to load x variable which I want to plot. So what I want to see the distribution of one of the variables. Okay, so let's see what so one of those variables like sepal length, petal width, etc. So x is equal to iris. I want to just fetch a single column, that is, let's say, petal width. And how do we create a normally distributed data? How does a normal distribution data look like? A bell curve, as you said. But how do we design that bell curve? What kind of chart we're going to use? Definitely we're going to use an histogram, because the histogram gives us the distributions. I want to say you create a histogram of my petal width, and my bins are going to be, I want to create some bins. Let's say I want to create a bin of, I want to create 20 bins, and the color is going to be blue. I want to give some titles. So if you see plt.title, and this is going to be petal width, and plt.x label. My x label is going to be, actually x label is nothing but, I would say it's bins, and plt.y label, I would say that is nothing but, let's say, frequencies. Okay, and I'm going to plot this. So you would see that we are looking like the same picture what we saw in the slide before, and we can check this for other attributes. So as I said, I'm not using a subplot. So let's do this for length. So for the length, we have this kind of a distribution with us, and so on and so forth. But if you see, the heading is still petal width, so we can go ahead and change. So title is something I would want to make it dynamic. So I would say, what are the options available in X? So I've got, what are the options available in X? X is actually a variable for me. So let's see what are the options available in X. Do we have name? It's not giving, so sometimes the intelligence doesn't work. It is quite slow, so no problem. So I'm going to say that instead of title, you make the title as dynamic, and you give me X dot. No, it's not coming. Actually, it's name. It's names. It's name X dot name, and I'm going to plot this. So now the petal length is matching up here. And so when we do this for all the charts, we're going to get a distribution something like this. So if you see, we all the distribution here we see are normally distributed. Okay. So what we have done so far? So far, we have created accuracy using the iris model dataset, using logistic regression, and using our Gaussian name base. Okay, I have not added one step into this, which is like confusion matrix. So guys, you are sure that you can do a confusion matrix by yourself? Do you want me to write a code for confusion matrix? So what is a confusion matrix? So confusion matrix is like I have created this model based on Gaussian name base or logistic regression, and now I want to verify that what is the amount of um, data which I have regressed actually is true. So Arun has a question. Can you please tell us a way to organize the data? That is correct, Arun. So actually, what you're asking the question that if you can load the data set and where can we have the data? Basically, this would be a part of pandas, Arun. So this is machine learning. So we are focusing more on algorithms, techniques, and way outs for machine learning. But what question you're asking is actually for the for the pre processing of the model. So I may not be able to focus on too many examples of importing data into like pd.read CSV or a pd.pdf or Excel or whatever. But if you explore the pandas documentation, you will definitely find how to import Excel data sheets. So Shruti says, please show the confusion matrix. You can please scroll at top of NB. Can we load the data in database? Yes, you can load the data. Neha says how to deal with outliers. I've done and working on that book. Thank you, Nagesh. So guys, I will insist you to please follow these steps. And in case if you, and I'm sure that for people those who are new to machine learning, these steps will not be immediately clear. The concepts would not be immediately clear. But as we move on a regular basis, I'm sure that you'll be able to get it. Sure, Arun, thank you. Yes, Pandas is the package. So basically, Pandas is the package for data assemble. So you can assemble the data in Pandas, you can transform, you can process, and you can bring it in a format or in a shape which is more suitable for analysis. Okay. So yeah. Now the other thing which we did last time is, some part of uh, we did like how to basically we check the accuracy of our model. So we have tested the accuracy, but how do I check that, the ones which I have tested and the ones which I have trained, what is some kind of a correlation between them? Can I create a matrix which is going to give me, create a matrix, create a matrix to form confusion matrix. Now confusion matrix is between what? Between actuals and predicted. And we're going to also solve mathematically today that, we have been given with some numbers and we want to actually predict those numbers in a very simplistic way. So create a matrix to form a confusion matrix between actuals and predicted. So actuals we can have on the x-axis and predicted we can have on the y-axis. So just like our from sklearn dot, so we did name based. Of course, we explored name based. We did explore linear models, but this is not a problem of a name based. This is not a problem of fitting a model. This is basically an issue of basically checking the accuracy or finding the metrics. So I'm going to say sklearn.metrics method. So this is I'm going to have an import confusion matrix. Now, this is very good for people who are looking at machine learning for the first time because this really solves this things makes it very simple. So mat is going to be a matrix which I'm going to create, and I'm going to use confusion matrix. Now, confusion matrix between what? Now, this is important step. I want a confusion matrix in my, so what is that? Y test, because Y is actually the dependent. So I want to test these dependents over my model, which is basically Y underscore model. Now, Y test and Y underscore model. So I'm going to say y test and y underscore model. Now, this is going to give us a confusion matrix for logistic regression because y test and y model were loaded with basically logistic regression. And I'm going to use a diagram which I had used last time also, that is sns.heat map. And heat map of what? Of course, the matrix which we just created. And I want some attributes like square. I want it to be true. I want C bar. I want C bar is equal to true. I will explain what these things are. And then, of course, I want some text, which is anode equal to true. And C bar is true, which is correct. So if I run this, then it should give me the output. So I don't need these colorful scale over there. So if you see how many kind of species we had in iris data set. So the dependent variable had 3 classes, right? One was Setosa and Virginica and versicolor. So basically 3 classes, that is 0, 1, 2. If you look at the x-axis, so let me explain for people, those who have not understood this part. So on the x-axis, we have species, the classes of species. On the y-axis also, we have classes. So on the x-axis, we have class of species. On y-axis, we also have class of species. Now, this is a confusion matrix which says, if you look at diagonally, so the diagonal means there is an intersection of the same class. So this one is 0 with 0. This one is 1 with 1. And this one is 2 with 2. Let's start with class number 0, which could be Setosa or could be versicolor or anything for that matter. So let's say class 0. So I'm saying there were 13 occurrences of class 0 in the test data set. There were 13 occurrences of class 0, and all 0 occurrences have been correctly classified. So all the species belonging to the class 0 is correctly classified. So similarly, for class number 1, there were 16 instances, or there were 16 records for this class, out of which 15 were accurately classified. 1 was misclassified. So the value in class 1 was given in class 2 here. So misclassified as class 2. And if you see at class number 2, there were total 9 observations, and out of 9, all were correctly classified as class 2. So class 2 to 2 is 9, class 1 to 1 is 15, class 0 to 0 is 13. I hope you've understood how to read. That's correct, Nagesh. It's 3 classes. So now I hope you're able to read the confusion matrix. Definitely moving forward, we're going to write more confusion matrix. Okay, so yes, there is. So Amir says, is there a table-based view of confusion matrix? Yes, there is a table view of confusion matrix. So definitely I can, change the parameters of confusion matrix and can bring that table. So, so Savleen says, Savleen says, can you please explain true positives and true negatives? Yeah, so this is something related to confusion matrix, Savleen. So true positive is basically the ones which are actually positives have been classified as positives. True negatives are the ones, and there is actually 4: true positive, true negative, false positive, and false negative. So true negatives is again the ones which are negative has been correctly classified as negative. And again, we have false positive and false negative, which is basically not true, but still classified as that particular class. So that's pretty straightforward, Salim. Neil says difference between validation data set and test data set. So basically, training data set is a validation data set. Or the training data set, and the test one is the one what basically which we test our model. Shreya says if we had more test cases, then accuracy might have been lower. Sorry, Shreya, I didn't get that part. So accuracy in terms of what? Okay. Okay, so I hope this confusion matrix is clear. And now, when moving forward, when we are going to plot confusion matrix, you will absolutely have no hiccups understanding that part. Okay. So as I had said previously, that I will be referring to some of the Wikipedia instances in order to understand the concepts of Bayesian classifier. The reason I'm stressing on Bayesian classifier because this is the fundamental to create classifiers using supervised machine learning. So Bayesian networks are widely used in many applications, okay, which you will see from the Wikipedia link, and we will also take some, inputs from the Wikipedia, like what is the formula, and how do we basically validate using the formulas, etc. And you will have to stick on to this session in order to understand the math which is behind this part. So we know that it's very easy to import, naive-based models in sklearn, or also import linear models in sklearn, and basically define the X test, X train, Y test, Y train kind of stuff over there, and basically get the output. But what happens behind the scenes? What exactly happens in a Bayes classifier is we're going to look at it quickly, and we're going to write a lot of codes also. I'm not going to focus much on Python codes, but very much sticking on to the fundamentals of data science and machine learning. So if you have any questions on Python scripting or programming, I will see if time permits, I will demonstrate that to you. Otherwise, I would recommend that the questions more or less should come from the machine learning side. So naive-based classifiers are simple probabilistic models. We have understood this using a slide which we have. But I want to directly jump on to a section which is called as Gaussian naive Bayes. And just below that, we have multinomial naive Bayes. Okay. Now, so far we know that naive Bayes is nothing but a based on Bayesian theorem. Naive Bayes is actually a classifier in a supervised machine learning. So if there are labels available in the data set, then we can utilize that training data set to predict new labels. That's basically the fundamental for naive Bayes. And same goes for logistic regression, but both have differences. We will understand that. But let's first come back to Gaussian naive Bayes. Now, I know that Gaussian naive Bayes, everyone knows that it is a naive Bayes. It is a distribution which comes out from a standard normal distribution. Now, this is an assumption, okay? And there is also another assumption in Gaussian naive Bayes, is that the features are independent of each other. So let's say when dealing with continuous data, I'm reading this part. So when dealing with continuous data, a typical assumption is that the continuous value for each class is distributed normally. So, so as we have discussed before. But there are two metrics which we are interested in Gaussian naive Bayes. Now, Gaussian naive Bayes, I can either solve it using the Gaussian naive Bayes function in sklearn naive Bayes, or I can actually solve it manually. So Gaussian naive Bayes algorithm we have seen, but let's see whether we can do it manually or not. Simple mathematics. This will trigger the reason for me to do this activity is that this will trigger a spirit of math in you, and you will also start relating, solving algebraic equations with the computation. So, for example, suppose the training data contains a continuous attribute. We will segment that by class, and then we find the mean and the variance. So what are the steps for Gaussian naive Bayes? The first is segment the data by class. So if we have 3 classes, we will segment the data by those 3 classes. And then we're going to compute the mean and variance for each class. So mean for sepal length, variance for sepal length, mean for petal length, variance for petal length in iris dataset, and so on and so forth. So let's say let mu be the mean of the values in independent X, and which is actually a class of C. So if you look at from our iris dataset example, we've got some mean of sepal length, and we've got some values of that X, variable or a record, and which is related to some class. The class could be setosa or versicolor or virginica, anything for that matter. And let sigma, this is basically the standard deviation. You can call that as a variance square actually. So variance, just for simplicity, we can call this as variance right now. And I'm going to directly jump on to the formula. Now you can take this as a magic pill. A magic pill means like you can just eat this in Python and start, getting the outputs. This is like a magical syntax or a theorem, you can say. In mathematics, we've been studying theorems. So this is also like a theorem, like prove that the probability of some observation value of V at a given class C, so is equal to 1 upon under square root of 2 pi variance, and then exponent of observations minus the mean value square upon the 2 into the variance. Now this might look and see quite daunting. I mean, you would say, why are we doing all these mathematical stuff? Now this is important, guys. I mean, I would still encourage you to stick on and listen to this, because if we understand this part, then the future solving machine learning will probably become easier. Now I want to understand from you, what is your understanding about probability? Now, as you know that Gaussian, the name base basically works on probabilities and posterior probabilities. So what does this mean? So this particular thing, P of X. So I'm saying, you give me the class K, whatever the class. What is the probability of getting a class C when the X is V? Okay. So what is the probability of class C when the value is V? So I hope you remember this equation, and this equation I think I have put down here also. Let's solve this using a simple problem statement. I will leave iris dataset aside right now, and then we will just go with another basic data set. Okay. So let's understand how we can use a Gaussian naive Bayes for gender classification. So if I give you this table, now can anyone tell me, by looking at this data set of first 5 records, that is it fair enough to apply a Gaussian naive Bayes on this data set? That is, there is a person given, and the person feature has got 2 classes, male and female, and then we have the corresponding height, weight, and foot for those persons. So is it recommended to use Gaussian naive Bayes in these scenarios to predict our person class? Shreyansh says, if we increase the number of test cases, the accuracy will increase. Yes, you're right, Shreyansh. But the accuracy will increase more when you increase the data set of your training model. Okay. Testing is fine. My question was, why everyone is saying no? My question was, when we look at this data set, the dependent variable is person, the independent variables are height, weight, and foot. Are we going to use, can we use the Gaussian naive Bayes algorithm to solve this problem? The problem is that we want to classify whether a person is a male or a female based on some given set of observations. Arvind says, yes, the data is normally distributed. Arvind, that is an assumption. So naive Bayes is actually a naive assumption of that. So we have not yet tested using an EDA, but yes, you're right. We will assume that data is normally distributed, and then we're going to follow the Gaussian naive Bayes over there. Tejas says, yes, we can use. Yes, we can use. Sujit says, Kunal, yes, we can use. Savleen, height and weight are not independent. I didn't get that part, Savleen. Why do you think height and weight are not independent? Kriti says, yes, because it's normal distribution. Prince Kumar says, yes. Neha says we can normalize the data. Yes, you can standardize the data, but we have not covered the standardization part in this example. Amir says, don't know. Siskal says, yes, we can. Ritu says, no, based on assumption that ladies will have feet size and height related. Whatever that could be, Khushbu over there, we are not very well known to that. Height and weight follow normal distribution. Pratibha says yes. Nagesh says don't know. Mahima says yes, we can. Ronak says yes, it will depend on how probability, how much it is correct. Nilesh, how can we say that looking at the data? See, Nilesh, how can we say by looking at the data is a good question. See, but we are using a Gaussian base and it is actually assumption that the data is normally distributed. Kavli says, don't know. Kemi says, yes, we can. Abdul says, can I get the PPT? Okay, Abdul, you'll get the PPT. So coming back to this one. Yes, of course, the answer to this question is that yes, we can use Gaussian name base. We can definitely use Gaussian name base because, firstly, we have not because the classifying class is binary, not because we have a male and female. What if we have male, female, or children? We can have another third class over there in this data set. Still, we will use Gaussian name base. It's okay. So Gaussian name base can be used when there is a possibility of multi-class classification. Definitely, we can use. But the Gaussian name base assumption is that firstly the independent variables should be continuous, okay, and the second assumption is that the independent variables should be normally distributed, and the third one is that the independent variables are basically independent of each other. They don't have any correlation between the variables there, as we have seen in the. Okay, so moving forward, I'm closing the question set box and I will come back to that after 5 minutes. So I have taken this small screenshot from a Wikipedia, okay? I've just taken this part from Wikipedia and we will use Python basically to solve these equations. Now I'm saying, now we saw that is the equation. So this is the equation 1 upon under root of 2 pi variance an exponent of my value minus the mean upon 2 into my variance. So let's say in this data set, I have successfully created the data, etc. And I would want to find out that if I pass a height of 5 feet, let's say if I pass a height of 5.14 and a weight of 138.57 and a foot inch of 6, then the class of this input data is going to be a male or female. That is what our basic, actual problem statement is. So let me add, so let's say insert table 1, 2, 3, 4, and let's say we want some records in that. And I want to decrease the size of this table and bring it some structure here. So delete rows, okay? So let's say I have some value here, 5.56, some value here is 155.4, and some value here is 6. And here is a question mark. Similarly, 5.66, 164.0, and this is 9. And again, the value here is a question mark. Correct. So I'm sure you know what I'm talking about. Now, I'm talking about handling unlabeled data, supervised machine learning. So what will happen if my height in feet is 5.56, weight is 155, foot is 6? What is likely going to be the output? Is going to be a male or is going to be a female? And that we can check using this simple equation which we have. I'm saying that what is the probability of a male at a 50%, 0.5, so 50% probability. So the formula here goes that we have to take out the probabilities of each and every independent variable and then take the product of those independent variables and then multiply with the actual probability need. I will make it simple for you. So how do we basically get this part? I'm sorry, I'm making changes in the presentation during the training, but that's fine. Let's say we have a probability of male at some into I have a probability of height given male into I have a probability of weight given male into I have a probability of foot size given male. Okay. I will compute these things independently and then take the product from the actual requirements. So I can change this from 0.5, I can make it 0.6, 0.7. I'm saying that you get me a probability at 50%. Similarly, the way we have this for the male, we will also have to get this for female. Okay, now please, uh, hear this out. Female, and then again, height of female, weight of female, and foot size of female. I'm going to get some output for this, right? And I'm going to get some output for this. If the output of male is greater than female, I would classify that into male. If the output of female is greater than male, then I will classify that as a female. Very straightforward, simple technique. Very straightforward and simple methods. Now, this will differ from other classification methods like logistic regression or something like that. But if you look at this problem statement, wherein we've been given with some kind of an input data and we want to find out some kind of an output data, then we're going to create equation in this manner for Gaussian naive-Bayes. Now, remember this, I'm talking only from Gaussian naive-Bayes perspective. I'm not talking about from multinomial naive-Bayes. Multinomial naive-Bayes is completely different than what we're doing right now. Similarly, logistic regression is completely different than what we're doing right now. And multinomial logistic regression is equally different than what we are seeing right now. This is only for Gaussian naive-Bayes. So I hope, so till the time we clear this part, you can ask me questions. And once this part is clear, I can go further, because if we are not able to understand this part, the further step is going to be a little confusing. So probability of male at 50%, probability of this height, probability of weight, probability of foot size. Now, but what exactly this syntax is, P of H/M? Can anyone tell me? It's basically conditional probabilities. Yes, Nagesh, it is conditional probabilities. Yes, Arvind, we have to calculate conditional probability. Above 1 in the first degree. Kunal says likelihood probability. That's very nice. Why probability of height above 1? That's correct, Ritu. Arvind says conditional, there is no audio. Now, is it there? There's no audio. Given height and predict, it's male. Absolutely, Himanshu has given the correct answer. So what does this mean? P of H/M is basically, you predict the probability of male given height. Similarly, you predict the probability of male given weight. You predict the probability of male given foot size. It's actually a conditional reverse probabilities is also. So, okay, so probability of height is given, etc. So we know now this is conditional probability, okay? Vishnu says, is it necessary to calculate probabilities with all features? Yes. If you are considering the variables in your training data set, then definitely you will have to consider all the variables into the equation. I'm closing the question box window and I'll come back to it after 5 minutes. So similarly, probability of female given height, probability of female class given weight, and for probability of female class given foot size. So if we try to solve this in Python, then we can come up with some observations. Okay. So the first thing is I have not considered any data set. I've just considered creating a simple data set over here. Now this can be a little difficult for people who are looking at it, but we can see how we can do it. So the first thing, I will import some pandas because pandas is something which you're going to need. Pandas and numpy as np. Now, how's the data set? We saw that the first part is for the persons, and then we have the height and the weight. So I'm going to take random some 8 observations. I'm going to create the data set rather than importing the data set from somewhere. I'm going to create this data set, and then we're going to apply some kind of a either logic or some kind of a algorithm to this. So the problem statement is, given some inputs, find the relevant class of those inputs. Okay, so we can do this either using Gaussian name base or any other method. In this case, we will be using Gaussian name base. So import pandas as PD, numpy as np. The first thing what we want to create is create the people class. So person is equal to, I said we want to create 8 observations, so male. So first 4 is going to be your male, and last 4 we can keep as females. What I'm doing here is I'm creating a list, correct? I'm creating a list, and I've created a list of persons. Now I want to create height, and I want to create foot. So let's say we're going to work on 2 observations, that is that is foot and the height. Now there is a reason for this, because when you include weight, sometimes the output becomes 0. I'll show you that in a moment. So we have created a list called as person, then we have to create different variables, and then we are going to combine them together using a pandas data frame. So I want to create use some random numbers. I'm going to say import some random, and I want to create a empty list of height. So if you see, this height is created in an empty list. So I'm going to use a for loop. So for I in range. Now guys, these are very simple syntaxes in Python. So if you have any issues understanding this, we can get into a basic core Python class. Now for is actually a loop. So I'm saying for every iteration in the range of 0 to 8, you do something. I'm going to say you create X. You give me round off of X, because, or don't right now, just give me random, which is actually random, and you give me a uniform distribution. I'm going to say you give me a uniform distribution of 5, starting with 5.0 on and ending with 6.50, and then what is our empty list? Height is equal to, height at append with X. This is basically I'm using it for, and then you print my height. If you see, if you've got some random value, so height is between some. Now height is basically is appearing in feet. So it's 5.25 feet, 5.98 feet, 5.1, but these numbers are extraordinarily large. So what we can do is, when it is giving this, I can say you round this off to a 2 decimal. So I've created a list called as height. Similarly, I want to create, that is foot size. Again, this is an empty list. Same, no difference for I in range. Range is actually getting me those iterations. Now, there's one thing which we need to notice, that when we use this uniform distribution for height, we are getting all the floats. But if you look at the foot size, it's actually an integer. Okay, 6, 6, 7, 8, 9, something like that we have done. So we will definitely use ranges, but we will not use random uniform. Instead of random uniform, we're going to use something else, which is x is equal to random dot give me random integers. So what this guy does, random integer returns random integer in range of a and b, including both endpoints. So I would say I have a foot size of 6 and 12. And I would say you foot dot append, it won't come because, sorry, foot underscore size dot append. Okay. And append with what? Append with x. And I'm going to say you print foot size. So how many observations? 1, 2, 3, 4, 1, 2, 3, 4. So I have a foot size range anything between this and this. So now we have successfully created our values. So we're going to put this into our data frame. And let's say our data name is data. This is going to be pd.data frame. And how do we put this into a data frame? Using the dictionary structure. Okay, so I'm going to say my first column name is person. And what is the variable? Person, because I have created a list of person here. Okay, so person, and then my second value is going to be height in feet, and the variable for this is height, and the other one is going to be foot size in inches, and the value for this is going to be foot underscore size. Okay, and I'm going to say data dot head. So you will see that we've got a nicer way of, we have put the data into a data set or into a data frame with the required data which we want. So we have created the data frame, we have the data frame. Now we need to implement certain things like Gaussian name base. But we can either do that using a Gaussian name based model, or we can do that manually. So I'm going to show you both the methods of doing it, and then we will see that in what method we are getting a better accuracy or something like that. Okay, but before this, it's important to understand that when we went to the Wikipedia link, it asked something about the variances, correct? So if you look at, so first we segment the data by class and then compute the mean and variance of x in each class. Now this statement is very important. So when we are reading this statement out, we need to implement this statement in Python. That is, first we need to segment the data by class. And what is our class? Our class is person, male or female. And then compute the mean and variances of these classes. So how do we do that? So there is a option called as describe. So we can definitely go with the describe method. If we don't want to go with the describe method, then there is a different method also. There is a problem in describe method is that in the pandas describe, we don't get basically the variance over there. So we might get the mean, but we may not get the variance over there. So let's see that. So going back to the statement, first segment the data by class and then compute the mean and variance in each class. So segment the data by class means you will have to group by. Okay, so group by. So let's say if I can do a group by, data dot group by. This is all, whatever we are doing is all part of pandas. I want to group by person, and I'm going to say you describe. So just going with the Wikipedia statement that first you group by the class and then find the mean and the variance. So if you see, I've got the count, I've got the standard deviation, I've got the min, max, etc. So if you see, there is the mean is not quite significant, but yes, there is good amount of differences in the mean um, for these values. So what? So the second part is to get the mean and the variance. So we will have to arrange this in a different way. So let me arrange this in a different way. So I'm going to say import statistics. Statistics doesn't mean that actually machine learning, but it's statistics um, functions. Okay. So I would say you get me data. First, you group it by person. Okay. And if once it groups by, you get me the mean of those people. So you will see that the mean of female height is this, male is this, foot size of mean is this, for male is this. You can see there is a significant difference in the foot sizes, the mean. Actually, the female's foot size is higher compared to male. In reality, this is not correct. It should be the other way. The male should have 10.25 and the female should have 8.50. But since we have created data randomly, this is quite imperative. So data dot group by. Actually, I have a list of, we can take the same numbers from Wikipedia also, but I've just created this manually. So person is a class, and what I want of this person, I want the variance actually, if you see. So height variance is quite significant, and if you see, even the foot variance is quite significant in both the outputs. So now what we want, so in order to solve, according to the Wikipedia definition, we have group by the class, that is male, female. We have taken out the mean for their classes, for each class, and we have also taken out the variance. And what is remaining now? Remaining is to actually solve this using the equation. Okay, so we have done that, segment the data by class and compute mean and variance. And we're going to use this equation 1 upon square root of 2 pi, etc., etc. Okay, so let's do that. Now I will have to import a library of math because I'm going to use some math functions. So I've imported math, I've imported statistics. Okay, but before I proceed, guys, I want to ask you any questions so far, and whatever we are doing, are you able to understand? Do we have any questions? Bhavna says, yes, I'm able to understand. Sandeep says it's good. Ramesh says clear. It is getting clearer now. Vijay says yes. Vishnu says so far, no doubt. Mahesh says I'm able to understand. Arvind says, can we different feature at a time in group by? Yes, definitely, Arvind. You can have n number of features in the group by. Nisha says yes. Why we used group by? Torsha is saying, why did we use group by? Raji, no doubt. Yes, able to understand and learning. Rajveer says, how can I import and package name sklearn processing import standard scalar? Uh, you have written the correct syntax, Rajveer. Anand says yes. Abdul Basit says it's interesting. Philip says yes. Nilesh fine so far. Jitendra, no doubt. Sujit says no doubt. We can get the PDF. Yes. Arvind, is there summary command or not? Summary command, Arvind, it's in R, and strangely, it is not available in Python. And summary command is my favorite too in R, but we can get away with that using describe in Python. Got the ideas of base, understand this, but not Iris. Pratibha says, I'm understanding this, but Iris is as good as this one, Pratibha. The only difference is that we have got species as a dependent variable over there. Rahul says, seeing it for the first time, getting a little bit familiar. Bhavni says, so far, so good. Error in module not found. Rajveer Patel says error in module not found. Rajveer, could you put the text of the error? Okay, so far, so we need three parameters: group by the class, mean by each classes, and the variance. And some people asked, why did we do group by? Group by, we did it because we want the variance. Actually, we can get the variance just like this. So data dot variance. So if you see directly, we can get the variance over here. But the issue is this way, we are not able to bifurcate the variance between the classes actually. So we can't see the variance for only female class or variance for only male class over there. Okay, so we can use this variance. I will use a scissor to cut this plot. So now we have all the three parts and start putting these things into our formulas. So what I'm going to do is I'm going to refer this particular thing, and this thing I've taken from Wikipedia. So you can very well refer the same link which I have it here, name-based classifier for Gaussian name-based. I've taken it from there. You can replicate the same scenario, but let me explain this equations. Once I explain this equation, it's going to be very straightforward and simple for you, and you can solve n number of equations like this. So I'm going to say, so what is we studied that we need to solve equation in this way, which is this one, right? It's not typing. So probability of male into probability of probability of class male given height into probability of class M given foot size. Correct? We want to do this. Similarly, P of female into probability of a class being a female when the height is given, and the probability of class being a female when the foot size is given. Guys, I've taken the data for this randomly, like random foot size and random height, etc. So, the accuracy or maybe the output numbers might be a little different, but we'll try to make it as relevant as we can. Okay, so this is what we have. This is what we want to find out. So probabilities, and then so once we get these individual probabilities, we're going to take the product of that and then multiply it with the actual probabilities for that. So let's start using the formula. So I'm going to create a variable probability of height for male. Okay, and let's look at this equation. So can you see probability of height? Probability of height or probability of a class male when the height is given. Okay, so probability, get me probability of male when the height is given. So let's do that. So probability of male when the height is given, and it is 1 upon and the expression. I'm going to come to this part. This is important. This one. What is this 6 here? What is this 6 here? Let's find out. Okay, so 1 divided by math dot square root. Have I not imported the math? Yes, math square root. And the formula is 2 into pi. So math dot pi. And then we have, if you see, the deviation square. So deviation square is nothing but it is a variance. So what is the variance for us? So variance for male height. So this is the variance option. So variance for male height is 0.044. So I'm going to say pi into 0.044. Okay. Now this completes our 1 upon under root of 2 pi variance. This part covers that part. And now we want to get an exponent over here. So how are we going to get the exponent is with the help of operators, double multiplication is nothing but the exponent over there, open bracket, minus, I've got some minus records, then again open bracket, minus of something. So this is again a height. So I'm going to say 6, okay, 6. And I'll talk about what that 6 is. 6 minus mean. So what is the mean of male height? So the mean of male height is 5.24. So I'm going to use 5.24 out here, divided by, sorry, minus mean. I put this into the bracket and it's actually a square if you see. So I'm going to say into 2. Okay, and then I have a division. And then division 2 into my variance. And what was my variance? 0.044, which was this one. I'm going to substitute here 0.044. So this is closing. So this is closing here. This is closing here, and this is closing. Let me run this. So give me the probability of class M when the height is given. There is some probability value has come up. Okay, we will not bother what value currently this is, because this value P of H is just we have got for this one right now. We also have to get for this one. Okay, so let's go for P underscore of foot size for male. Everything is going to be the same. So this is the variance, this is the mean, and this is the variance again. And what is this number 6? I will talk about in a moment. So foot size of male, 1 divided by math, square root. I will solve this using the Gaussian-Nabis method also after this one. Okay, so 2 into math dot pi into, now this is what? This is variance and this is mean. This is variance, mean, variance. So variance for, actually, variance for foot size. So male, variance for male foot size is 3.00. So this 3.00 raised to the power of minus, let's say foot size in inches. Let's say I have a value of 12 minus, this is the mean. So mean for male foot size is 8.50. So this is 8.50 raised to the power 2 divided by 2 into my variance, which is 3.00. Let me run this. So P underscore Fs underscore M. We've got some value. Now this value is very large if you see. And we're going to change this later on. We're going to consider this as a 5.2 rather than 5209 and all these numbers. We're going to consider that as 5.2. So I've got the probability of male height given, probability of male when the foot size is given. And what is our probability? Our probability is 0.5. Okay, so we're going to have 0.5, which is like at whatever probability we want at 0.5. So what we're going to do is 0.5 multiplied by 0.99 multiplied by, let's say, or simple stuff. So 0.99 into 5.2 we have this, okay? And if I do into 0.5, it's going to be in half, 0.5, 2.57, okay? Let's say this is 5.2, 2.57. This is actually male. Probability of a class being a male. Now, if the female value is higher than this, then we will classify this into female. If the female value is lesser than 2.54, we will classify that as a. So let's copy this. And this is going to be female. And so the height for female, what is the variance for the height for female? It's 0.226. So we'll replace this 0.226. And what is the mean for female? The mean for the height is 5.84. And this is again 0.226 because this is the female height variance. Female height variance 0.226. And also the value here is female height. We would want to say like classifying at 6 because ultimately we want to find out. So here also we had taken up at 6. Here also we're taking up at 6. Here it's 12. Definitely we will take it up on 12. And let's print this 1.00. Let's go with the other probability of foot size. And this is going to be for female, and this is again going to go for female. This is a manual way of solving it just to verify the classes, but Gaussian name base is anytime available for us to do this. So let's go for female foot size variance. So female foot size variance is 0.916. And what is the mean for foot size? Female 10.25. And 0. And last one is again a variance, 0.916. We got some value here, 3.41. Okay, so pretty straightforward. So we've got 3.41 into 1 into 0.5, and the value here is 1.7570. Actually, it should be at 0.5, 0.5 into 1 into 3.41. That's going to be 1.705. And the other one, probability of class being a male. So this value is much higher than this value. So you would see that the value of this class is lesser, 1.7, and this is 2.5. So I would say when the height is 6 feet and when the foot size is 12 inches, then it is likely to be a male because the probability of class being a male. So if probability of male is greater than probability of female, then classify as male, else classify as female. Pretty straightforward. Just for a quick verification, let's go back to our data, and we want to find out what if the height in feet is 5.51 and foot size is 8. So remember, height is 5.51 and foot size is 8. Let's do that. when height is 5.51 and foot size is 8. Okay, we're going to substitute these values. So height, pi, and I'm going to say instead of 6 feet, I want 5.51. Okay, and then the foot size instead of 12, I want it's going to be 8. Okay, so run this one, run this one. We got some value changes over there. So I'm saying you get me the probability of class male when the height is 5.51, which is here. Okay, and you get me the class of male for foot when the foot size is 8 inches. So let's go for, so what is the probability of this being? Now it is 2.574. So let me run the scan. This is run this, this is run this. This is 2.574, still the same probability. What about this one? When my this is 5.51, and then when the foot size is 8. So this is going to be something 7.60, and let's say what is the probability? It says 1.705. So probability class being a female is 1.7, and the probability class being a male is 2.5. And I think this is giving correct because the values which we have taken from the table, which was this one, 8 and 5.51, okay, and the person, actual person was male, and that's what our model is saying, that the probability is male. Let's see if we are able to do that for a female, that is 5.91 and foot size is 10. .91, let me just cross verify. 5.91 and 10, which is correct. So 5.91 and foot size is 10. So this is 5.91 and this is going to be 10. Run this, 141, and the probability of class being male is 2.574. Again, this one is sorry, 5.91, and the FS is 10. So you would see that the probability of class being female is 1.705, 0.5 into 3.41. Okay, no problem. Actually, it should be, yes. This is manually taken out. Just give me 1 second. So if I want to find the probability of class being male, this is going to be probability of, I'm going to use rather than 0.5 into 0.9, 141.92. So probability of a class being a male is coming at 70.25. Let's look at the, so this is 1 and this is 1.02, correct? And then this is going to be 0.51. Okay, still we are saying that the probability of class being a male is higher compared to 0.51, which is less than 1. So here in this case, you will classify the record set as male because we're getting a higher weight on the male compared to female. Now, since this is a very small record set of 8, definitely, and I've taken random records, so the accuracy is not going to be quite smart. But now you've got the method, and I can encourage you to create more such data tables and start creating your data set over here, or basically in a model. So let's go ahead and see if I would have done this using, Gaussian naive Bayes, then is there a way that we can still get this going in a Gaussian naive Bayes? I mean, definitely we can do that. So let's go and check the data. Data is actually this one, so no problem. I'm simply going to say cell, insert cell below, and then classify male, female using a Gaussian node base. And data.head is going to be this one. Okay, so let's go ahead and use the Gaussian name base. In order to do this, you will have to create our X data, which is going to be data dot drop. And I want to drop what? I want to drop person. I want to drop person, and then axis is equal to 1. So this is my X data which I've created. And X underscore data, let me just see. Yes, it is working. And I want to create my Y underscore data. The Y underscore data is going to be data, standing bracket, person. That's it. And then Y underscore data. Okay, so we have got 2D. So this is 2D and this is 1D. So absolutely fine. Absolutely fine to put it into the model. I'm going to run this back and cell clear. Okay, now we have imported the Gauss base, Gaussian name base, but we're going to do that again. sklearn.name base import Gaussian name base. Okay. And what is the next step? Model is equal to Gaussian name base as a function, and I'm going to fit here itself model.fit x underscore train, which is actually the data, and y underscore data, because that is a person. And run this. So we were able to successfully fit this data into our this one. Let's say I want to create a test. Test is I'm going to just create a test data, simple test data, x underscore data. And I just want one single row for that. Okay, I'm not looking for any different. I will also say test dot shape, and I will say just give me test. So I have taken actually one single record. Yeah. So I'm saying that you give me the class using the Gaussian name base. You give me the class of a person when the height is 6.49 and the foot size in inches is 9. Okay. And I can do this for most of this. So model dot, currently we're doing it only for one record, and it is test. So it says when the height is 6.49 and the foot size in inches is 9, then the output is female. Let's say if I use 0 here, okay, and then if I run this predict on the test, then it's going to get me male, 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 female, 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 which is absolutely correct because that was my input. And if we want to further look at this data nicely with our actuals and predicted, so I've got create a new column in my data frame that is predict, and it is nothing but model.predict of test. You give me data. So these are the actuals and these are the predicted. So can you see the actuals are male, 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 female, female, male, male, and female. So you could see that, using our manual methods, we could definitely get into some miscalculations over there. But if you're using a direct out-of-the-box Gaussian name base, we are able to accurately classify, 100%. So accuracy score of, what is that? Data predict. So we want basically I've not loaded that y underscore model. So yeah, so we can still take it, but I've not loaded that into the model. So that's fine. So yes, so this is basically the output of our actuals and predicted. Actually, it is a 100% accurate classifier, which has predicted the same output as inputs. But this is again, as I said, if you remember on day number one, I had discussed about a topic about wrong way of cross validation. So this is actually a wrong way because we have tested, we have predicted the same thing on our test data, and our test data is nothing but again data coming from X. So I can encourage you to look at this example and start creating your own test data, so that you're able to see the accurate classification of male and female. Okay, I hope guys, before we break for basically lunch, um, I want to know that you have any questions on this what we have studied. Um, okay, Sugandhi says, "Who's calling you?" Yeah, actually, I forgot to put my phone on silent, so let me just do that. Yeah. Amir says no questions on the workflow. It was perfect. So I think after this activity, we have considered, we have reasonably understood how Gaussian naive works and why firstly it is called as a Gaussian. The second part to this is that we have seen handling continuous data. Uh, the second part after the break, we're going to see we are going to see logistic regression, which is actually handling uh, binary output. So whenever we have a binary output, we can use logistic regression to do the job. We will see that after the break. What's the use of variance? Difference between data and data head. Please show the test data code. So the calculation done by us using formula is done by Gaussian naive. That's correct, Abdul. So instead of we going with a Gaussian naive, we could have done that manually, which I showed it to you. Manually, it's a bit of an error. It's better to go with standardized functions over there. So instead of doing it manually, I was just trying to explain you the science of the math behind that. So I hope there was so the variance and mean plays a major role. Uh, so once that is in place, we can use the Gaussian naive. You can split the test and train data using the train test splitter and in model selection or metrics basically. Sorry, in model selection. Jupyter Notebooks is already available on the workspace. Definitely, Arun, we will definitely try to look at more and more algorithms. This is just one way of looking at. Next part is logistic regression. We're going to do categorical classification. Nilesh says, why did we multiply all the probabilities in a manual method? I mean, that's how the probabilities are actually calculated. So if you look at the fundamentals of probability, you will definitely understand why did we do it. Okay, guys, so we can break for lunch, and I hope Himanshu says, why did you put 12 in line 14? And I put 12 over there because the whale is a new test data which we have. So I wanted to actually predict the probability of a male for a basic given height or foot size when the foot size is likely to be 12. So when the foot size is 12, then what is this going to be, a female or a male? Yes, why not? Because, okay, I haven't received the PDF. How should I access the PDF? Please help me in Jupyter. Can you please share the PPT? Today's first day. Okay, Bharat. So will you also share this notebook? Yes, this notebook should almost already there along with our practice. Okay, guys. So we can continue at 2:30, right after 1.5 hours, like after 90 minutes, we will continue and we will understand the questions coming from your side, and we will proceed further on to looking at different algorithms of classifications other than name base.
We can break for lunch, everyone. We'll connect back again at 2:30 sharp.
Okay, sure. Thank you.